Hi everybody, Chérif Matta here from Mount St. Vincent University. Today we're going to have a conversation about gravity or gravitation science. And it is my great pleasure to interview today Dr. Tina Harriott from Mount St. Vincent University and Dr. Jeff Williams from Brandon University, two very distinguished scientists that have made substantial contribution to the field of gravitational physics. So without further ado, I invite my two guests here to say a little bit about their background. So maybe Jeff?
Happy to start first. Yes, my background kind of changed from being in particle physics because I originally went into mathematical physics followed by particle physics, and one of the problems then was a problem describing spin. In fact, my doctoral thesis was to do with describing spin
by quantum mechanics.
Indeed it is, but by a topological method, by a classical topological method that would fit in with the theory of mesons. And that, in the end, turned out successful. But the interesting feature was that it had a spin-off, that the same topological structures, sometimes they're called kinks or twists.
You're using spin-off here as a metaphor. Has nothing to do with the quantum spin, right?
Exactly right. Yeah. Yes, you caught it.
Yeah.
And it applies equally well to general relativity. In general relativity, you have the same topological structures. Loosely speaking, there's something called a light cone in general relativity at each point of space. And as the light cone twists and tumbles over, it forms a topological structure, a little bit like a Mobius strip. And that existed, and that moved me into general relativity and resulted in my collaborating with Tina, in fact.
So moving to our other distinguished guest here, Tina Harriott. So what about your background?
Okay, thank you very much, first of all, for inviting us today. It's certainly a pleasure. As you can probably tell, I'm originally from the UK.
And so is Jeff, by the way.
That is indeed true, though we didn't know each other then. And the way I ended up in general relativity is quite different from Jeff's. I was a teenager when the Apollo moon landings were going on. And as a result, I wanted to be an astronaut, like many others of the day, I'm sure. And I quickly realized that I was the wrong nationality, so my parents, who were very encouraging from day one, bought me a telescope so that I could pursue perhaps space in a different way. And I was very fortunate that while I was working with the telescope in my garden one day, a lady drove by, saw me, stopped, introduced herself, and she was a fellow of the Royal Astronomical Society of Great Britain. And she sort of took me under her wing. I went with her every month to the Royal Society meetings in London.
I have known you for more than a decade. You never told me this story.
That's right. And so in many ways, I feel it's due to her that she encouraged my interest in astronomy. And then I went on to study a mixture of math, physics, and astronomy in two universities in the UK. And I ultimately ended up in Canada, where I met Jeff, as we both happened to be working at the Mount at the same time. And with our common interest, we became colleagues. That was almost 40 years ago, I think.
I was just going to ask. It was 40 years. And how did you actually meet, and what prompted these collaborations in the first place?
Well, I guess being the same university, we were actually in different buildings, but we were in the same department. But,
right.
You know, it's hard to work there without running into the person and, a few offices away. And Tina was in relativity, which I was starting getting interested in moving into. Tina was already there, kind of ahead of me.
Right. And here is a challenge, I guess, if you can say it. Can you put in a very simple words for the general public, the audience that is watching this program, what exactly is Einstein's general relativity theory, and what is the role of the so-called Einstein field equation into this theory? And why does it matter? And does it relate to the special theory of relativity in any way?
I guess I'll take that. And if I may, I'd like to just sort of step back a little bit and start with Newton, because I think many people will have heard of Newton and the story that he was sitting under an apple tree and saw the apple fall and came up with his
Is this
theory.
historically correct, this apple tree thing?
Well, it's not clear, but certainly several botanical gardens say that they have apple trees that they grew from the original tree. And certainly Newton's family had a farm, and he did go there from Cambridge during the plague. And so, you know, there are elements of the story that are true, but I'm sure he didn't have quite the eureka moment that people talk about, just seeing that apple fall. Anyway, so he came up with his theory of gravitation, which essentially says gravity is a force. And while it's very successful, it does have a number of issues. And some of them are practical, like, say, the orbit of Mercury doesn't quite work out correctly in Newton's theory. But there are also other issues, like there's no mention of time in the force equation. And so it was clear that there was some extra work or new theory that needed to be invented. And this role sort of fell to Einstein. And he had a totally different take on things. I think he felt that perhaps description of gravity through a force wasn't perhaps the way to go. He felt that really time had to be woven in with the notion of space, and so he came up with the idea of space-time. And he essentially came up with the very sort of simple idea in some ways that if you have a large mass, say the Earth, it will curve the space-time around it. And as a result, if you have something moving by that large mass, it will deviate from a straight line, and sort of the path it takes will then be curved. So that seems like a very sort of simple idea.
And what curves is the space-time fabric together,
Right,
like the four-dimensional space-time.
That's right. So he really felt that you couldn't talk about one without the other. And indeed, in the equations that we'll see in a moment, that they are woven together in a way that you can't talk about one without the other.
And in this slide, you have the Earth here curving what looked like a fabric, right? It looks like
Yes, that mesh is meant to represent the space-time background, and the Earth is then curving it because of its mass.
But of course, we can't represent this really because it's four-dimensional.
Right,
But here you're
right.
picking
We've
one.
sort of we've stepped down a dimension. But I think one of the most beautiful ways that we have ever seen to describe general relativity, which is Einstein's theory of gravity without an equation, is the following quote from a really famous relativist, John Wheeler, who was one of three authors of the so-called Bible of general relativity, shown there on the screen with the infamous apple. And his quote is that space-time tells matter how to move, matter tells space-time how to curve. And I think it's a very catchy phrase, but one that most people, I think, can understand.
It is very catchy. And this is the same John Wheeler that presumably coined the phrase black hole. Is that true?
Exactly. Black
Right.
hole, wormhole.
Yeah.
And in fact, he was quite a character. If you look him up, there are numerous quotes that are attributed to him that are all kind of very interesting.
Very, very important physicists, never won a Nobel Prize, but up there, you know.
Oh,
Right.
definitely.
Yeah.
Definitely. Yes, he and his two co-authors, they're probably the best known
And this is the
living.
book physically, like we can show. Yeah. So
There you go.
it's an enormous. Oh, so I have the task to lift it. All right, so here it is. Like this. This is the gravity book, and it's actually indeed it curves space-time itself, right?
Probably does.
So it's an
Yes.
enormous book full of. Oh, I shouldn't displace your notes in
Oh,
it.
that's quite all right.
Yeah.
Yeah, and John Wheeler founded a famous theoretical physics school for studying gravitation in Princeton, and this was one of the first schools devoted to general
And
relativity.
Princeton had all the big wheels of physics, right?
Of course, Einstein had
Einstein,
already been there,
yeah,
of course.
at the Institute of Advanced Studies there, right? Yeah.
So you mentioned also the actual Einstein field equation. So of course I felt that I would have to put it up in all its glory for you to see. And it's a very beautiful equation. I think mathematicians would appreciate its beauty, its simplicity in a way, and yet there's an infinity of solutions hidden in this equation. And going back to the idea of curvature and matter, the entire left-hand side of this equation relates to the curvature of space-time, whereas the right-hand side is the matter side. And so you can see how they're connected on the two sides of the equation there. Now, just to lead on to what Jeff and I do, I just want to draw your attention to that one term there that's in magenta called G alpha beta. That is actually something called the metric tensor, and it is the tensor that plays the central role in these equations. If you know the metric tensor, you can find out everything.
Because
about
this is
space-time.
the mathematical term that describe how the space-time curves, right?
That's right. It sort of measures the distance between two space-time points, which of course will change as the curvature changes.
Now, one aspect of this theory, of the Einstein legacy, let's say, you two are pursuing. What are you trying? How are you trying to push the envelope?
Okay,
Of
I'm going to
knowledge.
pass over to my colleagues. I'm sure you've heard me for long enough now.
Yeah, so the next person who arose in the history of general relativity that relates to us was a man named Ted Newman at the University of Pittsburgh, and he recreated Einstein's work in a completely different formulation. He called it the null surface formulation, and instead of being based on curved space-time, in fact there isn't space-time at the heart of Ted Newman's theory, rather there are surfaces. There are surfaces along which light travels. Maybe we should move to the next slide and see the relevant equation there. In fact, there are three of them. So these three equations replace Einstein.
Just the clarification, the NSF is null surface
Formulation.
not the National Science Foundations.
It's
Just
easy
a
to,
clarification.
easy to confuse
Yeah,
them.
okay.
That's correct.
Null surface formulation
Yeah.
of general relativity.
Yes.
And we see that big equation. Now, the difference between that equation and the Einstein equations is that, as Tina says, many solutions, hundreds, thousands of solutions of Einstein's equations are actually known and are in print. For the equation of the null surface formulation, it's defied solution for very many years. Eventually, Tina and I found a few solutions. At the moment, there are only a handful of solutions in this new way of looking at gravitation, and one has to not only solve the main equation, which is the long one at the top, one has to also at the same time solve the two follow-up equations. They can be described kind of simply. Maybe we should.
So this is an alternative to the Einstein equation that we've seen in the
Yes.
previous slide. It's not derived from it or coming from it. It's an
No,
alternative.
they're sort of mathematically equivalent.
They are mathematically equivalent. Right.
Yeah, maybe we should talk about the idea of the edge of space-time, because that plays into this idea of the null surface formulation. The simple way to think of it is if I take a flashlight, one here, and shine it across the universe, if we could imagine the universe had an edge, an end to it, a boundary, a wall, then we would see a pattern across the end of the universe. And in a sense, the universe can be made finite. This famous picture by the Dutch artist Escher shows what one needs to do. One looks at the angels and demons, and one sees this finite plate. It has an edge to it. And you look at the angels and demons, and in the middle they're quite large. As you move out, they get smaller, and as you move further out, nearer the edge of the plate, smaller and smaller and smaller. And eventually one realizes that what you have here are an infinite number of angels and demons. But there's a second way to think of it. All of the angels and demons, they're all the same size. Every single one of them is the same size, and that plate is stretching out to infinity. So you have your option to bring infinity into a finite region, or to leave it infinite.
It's a little bit like the sphere, right? It's an infinity but finite, because you can always go circle over circle forever, right? You can circle the sphere forever. Is that the idea, or is that?
Yes, it's very tied in with the idea of a sphere. In fact, to do it correctly in the correct dimension, you would have to go up one. The plate looks flat. We need this kind of spherical aspect to this.
Right.
And so the pattern that one makes at the edge, this describes reality.
So this picture reminds me is that a fractal eventually, because it's a repeated pattern at the end that keeps on repeating on a smaller and smaller scale? And
yeah, basically you have a sort of continuous rendition of a fractal. You've gone all the way to infinity.
Right.
And so you smoothed out those rough edges of your fractal. But no, you're absolutely right, of course.
Right. And what would be the fractal dimension of something like this?
I'm not very sure. But if we're assuming space is empty, then my flashlight beam just goes in a straight line, and the pattern is a circle, perhaps. But space is filled with galaxies, and clusters of galaxies.
So the light will deviate.
Yes, that's right. So the light deviates, swings around, the pattern becomes more complicated.
So it's almost like an X-ray diffraction experiment of a crystal. Like you have the X-ray beam coming and diffracts over the crystal, and form a diffraction pattern from which you can work your way back in order to reconstruct the atomic positions, in the crystal. But here you're basically saying something similar about the galaxies in a way that form some sort of a diffraction pattern, right?
Exactly analogous. Exactly correct.
Yeah.
By studying the pattern at the end of the universe, we can retrace our steps back and tell something about how the galaxies are, what the galaxies are doing.
Right.
And this is basically what that first equation of the null surface formulation does. It will allow you to calculate the pattern.
And of course, in the curved space-time where there are galaxies, these right cones will no longer be right cones. They'll have curved edges, and the circle won't be a circle anymore. But nonetheless,
like
if you can describe them, then you can find out everything about the space-time.
And these cones have one time dimension and two space dimensions, right?
That's right. We've stepped down.
So we have to imagine.
That's why it was called 2+1.
Yeah, we cannot imagine, of course, a real cone.
Yeah, a few people say they can imagine in 4 dimensions, but for mere mortals like me, it's impossible.
Okay. Right. So we can proceed with the slides, perhaps?
Well, I guess I can say a little bit more about what we have done in this field. As Jeff said, there are hundreds of solutions of Einstein's field equations. And the way that solutions are found normally is that certain simplifications are made. You might say assume spherical symmetry or something like that, and then you can come up with solutions.
On what basis do they make this simplification? What are the justifications?
For example, if you were trying to describe a black hole, for example, one might reasonably begin by saying approximates a sphere.
Okay.
You might make some assumptions about the nature of the matter, because at a certain scale, one might say the universe is homogeneous and isotropic, and maybe it behaves a bit like a dust. Perhaps the pressure is close to zero. So those are the types of assumptions you make in order to be able to solve those equations. So we took a sort of a similar approach when we solved the NSF field equations for the first time. As we pointed out, that first equation is rather ghastly looking. I mean, formally, it's a third-order nonlinear partial differential equation in 3 variables. And so it's not the sort of equation that you typically find in a differential equations course and what the solution is. So we made a number of assumptions, simplifications, in order to find our first solution, which we did exactly 10 years ago, in fact. And then since then, we found several others of increasing complexity as we got more familiar with the techniques. And as Jeff mentioned, the lambda there that you can see in magenta is what's playing the role of the metric tensor in Einstein's equation. If you solve that equation for lambda, which is what you're doing, you can actually describe the null surfaces. You can describe what those distorted cones are like. And then hidden in that sort of solution is everything you want to know about the space-time, the curvature, the matter, etc.
So what could be predicted from the solutions of this equation? Can you predict, I don't know, these distortions of Mercury, perihelion, or stuff like this?
I think it's more, maybe we'll each answer this, but I would say it's more that we could talk about, well, have we got a solution that has expansion in it? Does it have rotation? What does the matter tensor look like? Is it describing something like a black hole, or is it describing the whole universe? I think that would be probably more that the solutions we found would probably be more along those lines.
Okay.
Right.
Yeah, we can derive all sorts of physical features, as Tina says,
Right.
masses, densities, that kind of thing.
Right. And I think, Jeff, you told me once on a lunch that this equation is also has been also found in the 19th century by a mathematician.
Right.
The exact same form, yet one is totally an abstract mathematical equation, but here it's dressed up with a physical meaning given to the symbols that appear in the equation. Can you tell us a little bit more about that?
Yeah, this takes us back at least a century to France, in fact, to the village of Dolmieu. And this is where baby was born to the blacksmith's wife. So a poor family in a poor village in 1869. And that would be the end of the story. But France at that time had a system of school inspectors. They traveled the country with the idea of keeping the standards of French mathematics at a certain high level.
France in the 19th century was the epicenter of mathematics, let's say, or was it?
Absolutely right, yes, and particularly in pure mathematics and the development of mathematics, it was particularly France. And to continue with the story, the inspector was very impressed with the boy, the 9-year-old boy.
Cartan.
Cartan. How can I forget that famous
Eli Cartan.
Eli Cartan.
Élie Cartan.
Yeah, and so he arranged for Cartan for the young lad to go on to study in Paris in the École Henri IV, which is the leading school in
I think you have
Paris.
a picture of him, right?
And,
We do indeed.
yes, there's Eli Cartan, and as he aged, his mathematics improved. He studied at the Sorbonne. He became a professor at the Sorbonne. He invented whole pile of different areas of mathematics. One area he never got very far with, and that was the idea of classifying differential equations. He wanted to classify differential equations.
Like Tina a minute ago said something about the equation that we've seen that you're trying to solve.
Right.
And I cannot repeat exactly the series of words that she said, but maybe you can say it again, Tina.
It was a third order nonlinear partial differential equation.
Okay, and that's the kind of classification that he came up with?
Yeah, that was exactly the equation that he found, and he was discouraged, but he had a lot of other things to do. He invented differential geometry. He went and founded other areas of mathematics, so he left his famous equation behind. And it was in archaic notation, and of course the paper was in French, and rather old-fashioned French, in a journal that's not readily available these days. And so the fact was missed, in fact, at first by Newman and his people, that the equation that he was interested in was the same equation that Cartan had come up with and failed to do anything with or failed to solve. And that was the equation that we threw ourselves in, perhaps rather crazily and optimistically.
Wow. So I have a question. I mean, the theory you're working with is, even the most specialized scientists would tell you that this is really, really very difficult area of mathematics and of physics. But where do you see the difficulty comes from? Is it conceptual difficulty, or is it the impossibility of visualization of the concept that you are dealing with, or is it just simply complicated mathematics? Why is it considered so difficult and so foreboding field, the gravitational theory?
Well, I think for the NSF field equations, it's the mathematical complexity of that first equation. And even our most complicated solution that we found to date, there was still we had to make assumptions, in order to solve that equation. And at first, we didn't know whether the solution we would find would be in any way realistic. But in fact, we've been pleasantly surprised, I think, by the space-time that they actually describe. They've been somewhat realistic.
In fact, we're beginning to think that the easier ones, assuming that we are finding the easier answers, are natural in a way that they match the universe.
What guides you? Are you guided by by seeking beauty and elegance in the solution, or is it intuition that guides you in your research? What is the compass that guides your research in this field?
It's a little bit compulsive in a way.
Yes. I was going to say, now we've started it with, I'm stubborn, I want to solve it.
Good.
Because what we've done so far is in the 2+1. We'd like to step up to 3+1 dimension.
One is time, right? 2 dimension of space and 1 time.
So our current project, if you like, is trying to step it up a dimension to 3+1. Right. And for technical reasons, it has far more difficulty than just adding a dimension. There's mathematical complexity.
What prompted me to ask this question is because, of course, Paul Adrian Dirac, the famous Dirac, was quoted many times to have been guided by the element of beauty in the mathematical equation. For example, this is how he discovered his famous Dirac equation describing the combining relativity and quantum mechanics to describe the motion of an electron, for example. And in doing so, he discovered the antiparticles, the positrons, in the solution of his equation. But that brings me to another item here. Why does mathematics work in describing our universe? In fact, this question is, of course, has been asked many times, and most famously by the Nobel laureate Eugen Wigner in a 1960 or 61 paper, where he titled the paper on the unreasonable effectiveness of mathematics in the natural sciences. And let me quote something from this paper. Eugen Wigner closes his paper by stating the following. This is the last short paragraph in the paper. Let me end on a more cheerful note. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, listen to this one, which we neither understand nor deserve. And then he proceeds and say, we should be grateful for it and hope that it will remain valid in future research, and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. So why is it that mathematics are capable of capturing aspects of this universe, in your opinion?
Well, mathematics is a way of thinking, a way of systemizing thinking, but we mathematicians shouldn't be arrogant and think we've got a corner on describing the universe. I just don't think that's true. Artists make a contribution, poets make a contribution, writers make a contribution. It's a human endeavor. Mathematics seems particularly effective, perhaps at the moment, but the baton may pass to the artists in the next generation. Who knows?
Tina, any thoughts?
I think we are very fortunate to have this tool of mathematics to help us describe the universe. And I would say one of the motivations for us pursuing NSF, which has different mathematics to general relativity, is perhaps that we hope that this different formulation may provide insights, different insights. And I think that's true historically for different theories. You have different formulations that give you different insights. So, such as quantum theory. So in a way, I agree with him. We are fortunate to have this at our disposal, and perhaps we don't deserve it.
In closing this discussion, I was always wondered what are other interests of my guests? Like what do you two are interested in, other than the exact area of your research?
Okay, you can go first.
I can go first, sure.
And I think
There's
we have
even a
some backup
slide.
here with slides to
Yes.
show you what Jeff does, and he's not doing gravity.
Yeah, so it's the fern that we should be looking at here, actually. It's not the tree. This magnificent tree grows in Florida, and it grows with these ferns attached to it. And a botany friend of mine approached me recently, and we embarked on a project to understand the nature of the ferns and the connectivity, basically the topology of the ferns. And it seems that there are two types of structures that are common in root systems in general, not just for this type of fern or this type of tree. One's the herringbone construction, and there you see it. It has a kind of obvious name, herringbone. And the more complicated structure is the dichotomous structure, where the branches of the fern split. They always split in twos. There isn't a trichotomous. And the problem the botanist faced just a couple of years ago when he approached me, his name's Terry McGonigal. He's a botanist at Brandon University, and is that it's hard to identify a fern, whether it's dichotomous structure or whether it's herringbone structure, because they're usually a mixture. And particularly if it's a root system, perhaps a root system of a tree, you pull up some sample, and it's a bit of a mixture. And you want to classify your root, your fern, as a certain percentage dichotomous, certain percentage herringbone. What sort of thing do you need to measure? The thing that's easy to measure, you can imagine yanking up the roots, is the number of tips. And so here's an equation. I'm just looking at it now. It records the number of path. It records the path length for each branch of that simple root. Path lengths recorded by measuring the distance out from the start to each tip. So if
this
you
is
look,
this is topological path length, right?
that's correct.
It's not actually it's not a distance. It's a topological distance.
That's
so it's
right.
the number of connections to get you where you want to go.
Number of connecting segments, exactly.
Number
right.
of connecting segments. Thank you. Yeah.
And so as you go out to the first point, the first tip labeled 1, you can see there are 2 steps. And so looking at the chart, tip number 1, 2 steps. Look at tip number 2, 3 steps. And the relevant thing is the total path length for the entire structure. So if you add up all of the path lengths, you get P19. So that's a simple thing for a simple bit of a route. If one looks at the next slide, here one's looking at the dichotomous situation, a little bit different, and there are a few more things that need to come in. This is a particularly challenging chunk of route because it's not complete. The levels are not complete. You're going down as far as 1, 2, 3, down as far as the 3rd level, but on the right side you're getting no further than the 2nd level. So a formula was needed that would allow for incomplete routes. And if we go to the next slide, here's the formula. It comes in 2 bits. So one has the total path length, that's what one needs to calculate for the classification, and it's made up of bits and pieces. There's a Q in there, as you can see, a little bit complicated, and the next slide tells what Q is. And so my task as the mathematician, the mathematical part of the team, was to come up with a combinatorial formula. So quite nice, but very different from relativity. More akin to these discrete models of the universe that people are trying to create that abandon continuity and look at a sort of quantum discrete level. It's more in that spirit.
Very interesting, very interesting. And how about you, Tina?
Well, when I'm not doing general relativity, I work with a group of people at the Mount, including yourself, on a project called diffuse interstellar bands. And so these were discovered over 100 years ago by a lady called Mary Leah Hager. And what she was doing was studying binary stars. And you can see a binary star here. It just means 2 stars orbiting one another. And when you look at the spectrum from one of those stars, you notice that there are a bunch of dark lines below the stars that are moving periodically back and forth. Now that is totally understandable according to the physics that we know. It's called the Doppler effect. But what Mary Leah noticed was that there were some lines in that spectrum that did not move. And you can see there are 2 magenta lines there that are stationary when the other lines are moving. And this led people to believe that, in fact, those lines were not produced by the star, but they were produced in the intervening space between the star and the observer. And those in that intervening space, there are dust clouds. But the real mystery that has remained for over 100 years is what is the element or molecule that causes these unknown lines. And despite over a century of research, nobody has yet found an uncontested molecular source for these lines. And that's what our group here at the Mount is trying to do.
And this is a collaboration between yourself and Dr. Daniel Magis, as well at the Mount and at St. Mary's University, and Dr. Lou Massa at CUNY, Hunter College CUNY. And it's really an international effort, right? Led
and the beautiful thing about it is that we can involve undergraduate students.
We had a group of brilliant undergraduate students and graduate students from Mexico and Cuba. And it's a really international effort.
Yes. And I should say that here is a picture where the dark lines have been made white for effect, but there are now almost 600 of these lines known, and yet, as I say, nobody has yet found a source, but we hope that we're taking steps towards solving this problem.
Yeah, so taking from what you just said, there are 600 of these lines known, yet the source is unknown.
That's right.
And that's the problem.
And it's probably sources in the plural.
Exactly.
And it appears from our initial research that they're quite complicated molecules. They're not sort of something simple that you might expect. And
otherwise, it would have been solved much earlier.
Long
it
time
wouldn't have
ago.
remained a century as a mystery.
Exactly.
Yeah.
Exactly. So it's really nice to be able to return to my initial love of pure astronomy.
And I understand you have a Newtonian telescope or at home?
I do. Much like this telescope that you have here. It's a little bit bigger, but it's always nice to keep the connection with the origins of the subject.
Right.
Viewing the night sky and whatever.
And today we were supposed to have with us Dr. Lou Massa from City University of New York, and then 2 airlines have canceled his flights, so unfortunately we don't have him here. However, you, Tina, has a part-time job, if I may say. You're a pilot as well. No, it's not a job, it's a hobby. You fly plane with your husband, Dr. Steve McCarthy. Can you tell us a little bit about your flying?
Sure. Well, you probably remember that I mentioned at the very beginning I wanted to be an astronaut. I will never be an astronaut, but I decided that I would take one step towards that and learn how to fly.
But you discover much further things that you can see as an astronaut, because the astronauts only see 400, 500 kilometers above Earth, but you see billions of light years deep in the universe, right?
With the telescope.
With the telescope and with your formulae.
Right. That's true. But certainly I do enjoy flying as a pastime with my husband, and we were fortunate enough to live near an airport and have a small plane.
Which is here in the picture.
That's right.
Yeah, right.
Yeah, that's right. At DeBert.
And Jeff, you have another aspect of you that we don't know about, maybe?
I guess not. No, I do enjoy writing. And so in my spare time, I write short stories, working on a novel. In fact, this one of my short stories was published in this book of beach reads, so-called, sort of thing that a person would take to the beach for kind of fun. And it plays into doing theoretical physics. It plays into relativity because the skills that come with, that you have to learn to write a short story, let's say, are very useful in writing a paper, being clear. Yeah, selecting your words properly, thinking about the reader. Many people who write scientific papers never think very seriously about the reader.
They are supposed to be published, not read, right?
Absolutely right. Yes.
So, well, thank you very much, both. It has been a true pleasure to have you, Jeff, in Halifax again, and Tina, of course. And thank you very much for watching, and we'll see you next time.